Assalamu alaikum. I welcome you all to this short tutorial on Lab 3. As you know, we had a small tutorial for Lab 2 as well. So this is the same pattern as that. I'm just going to go over some commands that might be helpful in this lab. It's not necessary that you have to use these commands. It's just that perhaps at some point these might be helpful. So we're just going to give you a rundown of some of the basic commands. Right. So now I coded some of the snippets beforehand to save time, but I'll be going over these commands. So first we're going to look at identity and zero matrices. Identity matrix, as I'm sure you all will be familiar with, is a square matrix n by n, which has ones at its diagonal. So identity matrix command is simply np.identity, and the argument is the dimension. Again, we don't need two different arguments because it's always going to be a square matrix. So we just need one of them. So 5 just means we'll have a 5 by 5 identity matrix with ones at its diagonal. And zeros is a matrix which consists of all entries which are zero. It's not exactly a null matrix, but for example, if you want to make a matrix in which you want to update every value later on, you don't want to append or you don't want to add on vectors in the matrix. You have a predefined fixed matrix and just need to alter the values. So just make a zeros matrix and keep on alternating the relevant index values. That's one way you can use it. It's a roundabout way of doing it, and there are better and efficient ways, but in case you need to use it. And np.zeros creates a zero matrix, and it has no limit. It can be a 1D matrix. For example, you just give one dimensions here, it's going to be a vector, or the argument here is a tuple, and these are the dimensions. This means it's 2 by 4 zero matrix. I can make it a 3 by 4 or anything, but this tells us dimension. It can also be 3 dimension or further on. So np.zeros is the command you want to go for if you're making a matrix consisting of all zero values. And let's check this out. Yeah, as you can see, this is an identity matrix 5 by 5 with ones at its diagonal. And the zero matrix, which is a 2 by 4 zero matrix, all entries are zeros. That's what we're going for. Yep. Now moving on, exponential powers. Another thing you might not need in the lab, or perhaps it's just a neat thing to know if you're learning to code in Python to begin with. For those who are familiar with it, they can skip this because this is a very basic function. For example, if you have some variable, you just need to square it or cube it or raise to power 10 or 11. Normally how you write it, and so for example in MATLAB how you use it, you use this operator. This means 2 raised to power 5, but you cannot use this because this means a bitwise operator. It has a different function. Sometimes if you want to square, you can just use this as well. However, what I'm going for is a simple function. Because I use this library math, this allows me to use a function. Yeah, this library, right, import math. This allows me to use the function POW, which stands for power. And the first argument is the base that I'm going to be raising to the power, and second is what power. So this just means this is x squared. This means it is x cubed. I can place x raised. This means x raised to power 6. So what I have is x equal to, this is y is equal to x squared, and z is equal to x cubed. We'll just run it and check it out here. 248 x squared x cubed. Perfect. I have increased the font here, so I hope this is a little bit more visible. There was complaints that last time perhaps it wasn't so visible, so I hope this helps. Now let's talk about pseudo-inverses. We talked about pseudo-inverses in the previous tutorial as well. When I was just touching upon inverse, I just gave you a little preview of what pseudo-inverses is. Now you have actually studied them in your lectures, and you know pseudo-inverse exists for a tall or a wide matrix. If a tall matrix, then there's left pseudo-inverse. If it's a wide matrix, there is right pseudo-inverse. Because it's not a square matrix, you can't simply take an inverse. Now, the thing about programming in Python, the neat bit is that you can make a matrix. For example, I've made a matrix here. I've made an NP array, 2D array, which is 2 by 4, as you can see here. It's a 2 by 4 matrix. Now, I don't need to specify if it's wide or tall. I don't need to specify different commands for left or right inverse. Like I said, I can just use the same command, np.lenalg.pinv, which stands for pseudo-inverse. If this was the command for normal inverse, this is just the command for pseudo-inverse. That's all you need to do. And this is going to see itself if A is tall or wide. You don't need to specify it, and it's going to take the relevant inverse. So A underscore dag has the A dagger, which in this case would be the right pseudo-inverse. But nowhere I have specified it's wide or right pseudo-inverse. So you don't have to worry about that while you're programming and using this command. Yep. See, the A dagger is 4 by 2. A dagger is a 4 by 2 matrix. Obviously, it's not a square matrix, and the values are 0 0.50, 0, 0.5, 0 0.50, which you can check. Right. This is how you take pseudo inverses. It's a very simple one-line command. Now, let's talk about norm. You've already studied norm in the first first few lectures. Euclidean norm, as we'd like to say, is the L2 norm, Euclidean distance. So what you don't have to program a lot. You don't have to go just take a matrix, take its transpose, multiply just to get an L2 norm. I think there's a very neat function for it. And usually what we do, as you'll see in the lab as well, usually what we do is we usually calculate the error as the distance between our predictions and our true values. And usually the error is the difference, L2 norm squared difference between our predictions and true value. So you can compute all that, but what I'm going to just give you a brief intro is, for example, if we have two arrays, we have one NP array and another array, obviously the same length, otherwise you can't compute the difference. The function is np dot linear algebra and lang dot norm. Self-explanatory. Now the first argument is the norm that you want to calculate. I can just write A here. This will just give me the L2 norm squared of A. I want to calculate the norm of A minus B. So this is the argument, the expression that will go inside the norm. The second argument is which norm do I want? This is L2 norm. If I write this means L1 norm. This is L3 norm. So we need L2 norm. So we write OR is equal to 2. And then this is just squared. So my error is just the L2 norm square of A minus B. That is my error. So this is just a single line command to calculate error instead of just reiterating and taking transposes and multiplying, doing matrix multiplication. You can just simply do this. Yeah, works like a charm. This error is the error. That takes care of norm. Oh, one more thing you'll be figuring out when you're going through the lab at the end, that you need to plot on the same figure. So obviously you're all familiar with how to plot diagrams and MATLAB pyplot and everything, but just in case if you struggle plotting it on the same diagram, I'm just going to give you a rundown. I'm not going to actually plot here. I'm just going to go through the commands. You just make a new figure through plt.figure like this, and you just do add underscore subplot. Right, this is saved in figure here. That's why I used, if I stored it in fig, I would just make this fig. I just added a subplot. Just follow these commands. You don't have to worry a lot about what exactly are the niches and what are different kind of arguments it can take. Just use this argument and save it into ax, sort of like an axis. And if you just keep writing this command, ax.plot, and right now you don't have to write this, you have to actually write what you want to plot. For example, if you have variables x and y, you just write x.plot x, y. And for example, if you want to indicate them with a full stop or with a cross or anything, marker. This is just normal plotting. You have two variables, you just say x.plot, and then you write x.legend location upper left. This means that this plot will have a legend on the upper left of the figure. And then you go about doing other calculations and simply do not write other figure or PLT commands, and then just write x.plot again for another variable. For example, now you were taking the relation between x and y, and now you wanted x and z, right? So you say x.plot x and z, and again the legend in the same location. So what will happen is you'll have just one figure, and these, whenever you write x.plot and these things, they'll be plotted on the same figure, overlapping, and all the legends will be accumulated at the top left. So this is going to help you when you're plotting your training and testing results in the lab. So think along these lines. Obviously, there are other ways to go about it as well. So, but this is particularly for those who are very, very new to Python and are not quite comfortable in plotting. So you need to focus on the lab and getting the results. If you're just stuck in plotting and how to get it on one diagram and instead of spending a lot of time on debugging, use this kind of code snippet, and this is going to help you out. And if obviously there are other ways to go about it. You can use them if you're much more comfortable. So there's not a lot of technical stuff in this lab, but this is some of the stuff I thought that might be helpful. Some already predefined commands that can help make things a little easier. The rest of the lab, problem solving, what variables to take, how to make matrices, how to formalize them, where do you need to take the dagger, how to find the least square solution. That problem solving is up to you. It's explained extensively in the lab as well to help you out. But this is some commands that can help you on the way. If you have any concerns or issues, feel free to contact us. Hope this helps. Thank you.